This video covers the basic physics incorporated in badminton. We will cover the projectile motion of the shuttlecock during its trajectory, energy transformations, and the frequency fluctuation due to the tension of the racket strings for the basic badminton shots. First and foremost, badminton is a sport where players use rackets to come in contact with the shuttlecock or birdie to make its way to the other side of the court back and forth. Badminton shots often create parabolic shapes that can be seen as a projectile motion. It is best seen with the long, clear shot. Let's assume a shot is taken at 100 kilometers per hour at a 45-degree angle with no air resistance. With such shot, we can calculate that it would take 4.0 seconds to complete its parabolic flight using one of the 5 equations of kinematics. With this, we can calculate the range at which the shuttlecock can travel, which is 7.88 times 10 to the power of 1 meters. Additionally, we can also calculate the velocity at which the shuttlecock will be traveling at the end of its flight. The final velocity of the flight is 27.8 meters per second, forwards, 45 degrees downwards. This can be done by using one of the 5 equations once again. The law of conservation of energy states that energy cannot be destroyed or created. In relation to badminton, as the shuttlecock travels across the court, potential energy increases as the height increases and kinetic energy increases as the shuttlecock falls, while the total energy stays the same. Therefore, no energy is lost. The energy obtained by the objects which work is done is known as mechanical energy. We can prove this law by using drop shots. The calculations for total mechanical energy can be done by finding the sum of the shuttlecock's potential and kinetic energy throughout its course. Using this equation, we are left with both a total of 8.7 times 10 to the power of negative 2 joules. The height of the badminton net is about 1.55 meters. At that height, kinetic energy is 0 joules. When the shuttlecock reaches the ground, all 8.7 times 10 to the power of negative 2 joules of potential energy from the top of the net is now converted to kinetic energy, still at 8.7 times 10 to the power of negative 2 joules. Now, moving on to the tension of the racket. Higher tension provides more control and the vibration increases due to its rigid structure, while the lower tension provides more power on clears and smashes with less vibration. The lowest string tension recommended, according to Yonex, is roughly 17 pounds, while the highest is 24 pounds and up. Note that too much tension may overload the pressure, resulting to the damage of the string and racket. Through using the wave speed equation, we gain an understanding of how the tension affects the pitch of the sound. For a high tension of 28 pounds, we will start off finding linear density of string using the average string length and mass. Then, we plug in the tension force and linear density, giving us 500 meters per second. As for the low tension of 17 pounds, we will plug in the values based off the string, resulting us with 386 meters per second. Now, listen to the audio carefully for the differences between the high tension string and the low tension string during the most powerful shot in badminton, the smash. This proves that the higher the string tension is, the higher the wave speed is, meaning the frequency is higher and lower wave speed and frequency for lower tension. To conclude, badminton is a competitive sport where players are endorsed to using physics to achieve a pleasurable victory defeating their opponent.
I love you, Mr. Nguyen.